Okay. All right, we have basically concluded last week with a review, and then we did the in-order pipeline, and then we talked about branch prediction. The next big improvement in computer architecture was out-of-order execution. Instead of doing things in 5-stage pipelines, one after another, aka in order, it kind of just takes your instructions, throws them out, and then they complete when they complete, and then reassemble it in the end. So a more realistic pipeline, or more likely what it looks like, and this is nowadays, pretty much every processor does something similar to this, unless it's a really small embedded chip. You still have your instruction fetch and your instruction decode, but after that, it sends it out to whatever functional units you might have. For example, if you're doing an integer, it just goes to an integer unit. If you're going to a floating point, it will go to a floating point unit, which of course takes multiple stages to complete. You got an adder, and then you have a divider as well. And then it reassembles back to memory and right back. All right. Why do you think this is advantageous?
The parts can specialize.
Figure out where it needs to go.
Parts can specialize. I kind of like. I like that. What's your idea?
Yeah, it's like figure out where you go. Actually, I'm just.
No, take a guess.
Let's figure out where it needs to be.
Figure out where it needs to be. Okay. Well, beforehand, this whole middle part was just the execute stage, right? But now it's broken up the execute stage. If you look at it, the execute stage can now take a different number of cycles depending on what instruction is. But more importantly, by breaking it out, you might send a divide instruction, have that going. While that divide instruction going, maybe you can send out a multiplier and adder while that one's still moving along. Maybe send up to an energy unit as well. And then when they complete, you reassemble it at the end and then do right back. So the big point here is now it's going to even help you even more with doing instruction level parallelism inside the execute stage. Okay, so there's a different, if you read the book, by the way, we're in chapter 3 of the book, and today I will be assigning homework from the first half of that chapter. Ooh, yeah. There are different dependencies. The first dependency is the only type that we've talked about, and we're talking about a true dependency, or what we called beforehand a data hazard. And that was a read after a write. For example, in this one, if we are writing, just for example in this code, writing to 3, and then we try to read afterwards, there'd be a read after write true dependency, because you remember in the 5-stage pipeline, that wouldn't be written back for at least 2 or 3 cycles. So that's this dependency that back then was a problem. Now, there are other types of dependencies, and these do not exist inside of an 5-stage in-order pipeline, but I want you to at least be familiar with these, so when we go into in-order, you know what to look for, aka problems that are coming up. So another one's a write after a read. So if you try to write to a register write to a register after you've read from it, that's called the anti-dependency, aka it's the opposite of the true dependency. This one may not make too much sense for now, but a write after a write is an output dependency. If we're doing out-of-order execution, why would write after write be a dependency problem?
If you do them out of order, invent the second thing first.
There you go. Is that a problem with in order? No, because you're forcing it to be. But now if you're in out order, you have this extra issue that comes up. And then what do we have? A read after read? Usually not a problem.
Rar.
The RAR. All right, so what is it? It's a write after write. Okay. This one comes up because maybe you haven't fully read the register, and then something in the future gets written to it before you got the old value in there. For example, let's say that this one had a dependency above it, so it couldn't execute, but it was able to execute the NAND first before it executed the add. And if that NAND completed before the add could be issued, then that would be another dependency issue. Does that make some sense? By the way, Bart, if you have a question, go ahead and message me. Hopefully it'll give me a little ding when you have an issue or a question. Okay, out of order execution. Variable latencies make out of order very desirable. Integer add usually takes 1 cycle to complete. Integer multiplication takes 20, and division can take all the way up to 50 depending on your processor. And then floating point, I think an add was about 3 or 4 cycles, and then multiply could be about 20 or to 30, et cetera, et cetera, et cetera, et cetera. So a lot of these instructions have varying latencies inside of execute. So by being able to pipeline all your different stages inside of execute, you can increase your clock rate even more. So this is very, very desirable to do some sort of out of order execution. But the question is, how are we going to prevent the new hazards, which is write after read and then write after write? How did you pronounce that last one?
Wow.
Wow. Good job. And then, of course, how do we deal with variable latency? Now the write after read, the read after write, aka the data dependency we had last time, is actually going to be a little harder. So we're going to go and look at the whole stage of how these instructions look like. Your add only takes 1 execute, so it's just the standard 5 stages that we've been used to. But a multiply is going to take more. In this instance, looks like 7. So instruction fetch, decode, execute, 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 memory write back. Well, now if you're trying to divide, remember this is your read after write, and he's waiting on the 6, he's got to stall for a while before he can start executing.
That sounds fun.
It is fun. Luckily that add, we're okay. We're okay to issue the add, but we can't write it until this guy's completed. So we have a little weird dependency right here that may be a problem or may not be. In this case, I don't think it is actually a problem. Oh no, in this case it is a problem because you don't want that 7 to be written before the previous divide actually reads it. Yeah, you see that error right there? Because remember, this is now out of order. This guy is stalling. This instruction is being issued. He's going to complete before the divide can even begin executing because the divide's waiting on the instruction ahead of him, before him. So that's the what was it? Write after read error. And then now this sub 8, of course, is again. The sub is going to execute, but he's writing to 8, which he can't write to yet because the divide is also writing to 8, and that hasn't been completed yet. So to keep everything semantically the same, he would have to wait over here until this guy completes, and that's your write after write problem. Okay. Make a little more sense?
So there's order working the way down.
Yeah, these, when as a programmer, you write it, this code, this code, this code, this code. So the contract with the processors, you're going to execute these one after another. But we want to try and increase performance, so we're going to actually execute them out of order, but somehow make it seem like they're executing in order logically. And the reason we want to do that is because this multiply execute takes a long time. And notice that while that multiply is executing, we're able to complete the add and the subtract, while multiply still hasn't finished. So we're able to find instructions further down that we can execute, save some time later on in the processor, and then we just need to figure out how to fix it later on. So this is also a good example of why out of order is advantageous. Any questions on this example? Oh wait, I need to take that off. One moment.
You use Skype? Gross.
I had to in my previous job. Apparently I never uninstalled it. Okay, hey look. What does that look like?
Very old computer.
A very old computer, yeah. So out of order execution is actually not that new. It came out in the 60s. And it hasn't, the basis behind it has not actually changed that much in recent years. It's just, it came out in the 60s. It wasn't fully adopted until the late 90s. That it became prevalent everywhere. And this is the first machine that did out of order execution. It's the CDC 6600. But its technique was called scoreboarding. Now, Scoreboarding is going to be the first technique we will study for out-of-order execution. It's probably the more intuitive way of doing it. And then we're going to look at the Tomasulu method, which is what pretty much every modern processor uses nowadays. So there's two different techniques. First, we're going to look at scoreboarding, then we're going to look at Tomasulu. So this one's a bookkeeping technique, and this probably makes intuitive sense. We're going to issue instructions and then basically keep a record of, hey, is this instruction ready to commit? Can we actually issue this one yet? As well. So there's really two questions that this one's going to answer. Can we issue it and can we complete it? So the out-of-order issue excuse me, actually divides the decode stage into first issue, decodes the instruction, check for any structural hazards, and then read the operands, where we wait until no data hazards, then read the operands. So what type of how are they fixing their control hazards, or their data hazards, sorry, here?
Waiting until there's none.
AKA they're
Looping.
stalling. So they're choosing stall for fixing all their operations. Now, in order, was that the fastest way to do it? No, but it does fix the situation, which is why we're studying this one first. So it's like beforehand, we're studying, okay, what do you do if you just stall it, but maybe you can maintain out of order? And then Tomasulu is going to show you how you can actually do a cool trick in order to make it avoid a lot of these stalls.
Trick.
Oh, it's a cool trick. It's a pretty cool trick. All right, dates back to 1963. Great. They execute whenever previous instructions and there's no hazards. So scoreboarding is really just going to say, can we issue this instruction yet? And once it can, then it dispatches it. It makes it before it dispatches it. It waits till there are no hazards, and then it actually reads from the register file. So it's in order, out of order execution, and out of order commit or completion. There is no forwarding, imprecise interruption or execution model because if you try and interrupt it, some of the instructions may have already been completed that shouldn't have been. And we're not going to talk, we'll talk briefly about what we can do about that later. All right, what does it look like overall? Well, the nice thing about out of order is you can have a bunch of different arithmetic units. So this one has two floating point multiplies, a divide, floating point add, and then usually one integer unit. Or this one has one integer unit. The scoreboard, which is fetch and issue, is going to take care of getting the instruction and making sure it can actually issue it. It is going to talk to the registers and when it needs to and read from them and then send them out to be executed. You okay, Matt?
Mm-hmm.
So out of order completion, we do have write after read hazards and write after write hazards. But what does scoreboarding do? It stalls right back until all previous issues have been read. And you only reads registers during the read operand stage, which is inside of decode. Again, this is stalling. If there's a write after read issue, it's just going to sit there until that data hazard goes away before issuing it. For, let's see, write after write, you detect and stall, again, issue as well. So this guy, scoreboarding is really just going to stall most of the time when there's an issue. But you still want to see if you can fill up your execution units with any type of pipeline instructions, integers, or floating point. Yeah, and the reason why it's called scoreboard is that if you remember down here, there's a scoreboard that just keeps track of all these issues. Yeah, okay. Let's go look at a better picture. There's no forwarding in this data model, so keep that in mind. All right, so the 4 stages, sorry, I mentioned that back here. Instead of ID, execute, mem, and write back, it has its own internal 4 stages, where execute can take a varying length of cycles. So issue, of course, you decode just like you would. Issued in program order for hazard checking. Don't issue if there's a structural hazard, just wait. And then don't issue if instructions output depended on any previous issued but uncompleted instructions. In other words, there needs to be no problems before you send this guy out. And then once there's no hazards, then you go to the second phase of the decode where you actually read the operands and then send it out. All right, so the execute, once you have confirmed that there's no hazards, you can go ahead and dispatch it to the execute. The execute, of course, is going to grab the information. The information is correct because there's no hazards. And then when it's ready, it'll notify the scoreboard. This also includes memory operations. Excuse me, and the write result, yeah, when finished execution, stall until no war hazards with previous previous instructions. All right, the scoreboard used in 6600 would stall pretty much on any war, although you could hook up forwarding similar to what we did last time. All right, let's see, 3 parts of scoreboard. You have the status. I don't know why it's always printing the one at the bottom. Instruction status, what state the instruction is in. Is it being executed? Is it waiting to be written back? Is it being decoded? Functional status of the units. The scoreboard needs to know how the units are doing. Is it busy? aka the FP multiplier is actually multiplying something. What operation is it? What's the destination register for it, so it can actually check for write back or any type of write after write issue. Any source registers that it's using, so it knows what it's trying to read from. And then, let's see, functional units producing source registers, right. The reason this flag is here is if another instruction ends up coming saying, hey look, I'm waiting for this functional unit to complete, you can flag it as well. All right, this makes a lot more sense when you actually put it all together. Okay, and then flags telling you when they're ready. All right. This will probably help solidify what's going on. So here's the full scoreboard. Here are the instructions. Upper left, we're going to execute, issue, the read operation, execute, complete, and the write result. These are going to be our functional units. So our processor has 1 integer, 2 multiplies, an add, and a divide. And these are floating point, and that's why there's 4 of them. And the integer unit basically does everything. Okay. So what's on the right is the precise explanation of the bookkeeping. What's on the left, or on this column right here, is essentially what we're doing to think about it. So we're going to go into an example. Issue. If the pipeline is available and there's no write after write possible, is how long you wait on issue. Read operations, you're just making sure that, hey look, you can actually read them both. And then write result, just make sure there's no war hazards. No earlier instruction has yet to read the destination reg. Okay. How you doing?
Swell.
Really?
Yeah. I saw there's about 200 of these things.
Oh,
Yeah.
you feel even better, don't you?
Yeah.
Oh, that's good. I'm glad. Don't worry, we should get done on time. Okay. Load comes in. Can he be run? Yes, there's no issues. We have no instructions running. We're ready to go. We'll issue it in cycle 1. We put it down here. It's an integer instruction because you're usually base plus offset, so you got to load that and then go into memory afterwards. So it's an integer. It's a load. Destination F6, that's where it's going. Source is R2. There's that K. And then if the FJ, is it ready? Let's see. Yes, because we're not writing to it. All right, clock 1. And where's the F6? Oh, F6 is the register up there. All right, going to 2, it reads the operands. Can we issue the load? It answers for you.
Oh, no.
No.
Yeah.
Why
It's
not?
this. That integer pipeline is busy.
Yeah, that integer pipeline is busy right up here. We can't load that guy, so we're going to wait.
Okay.
All right, it's done. Issue the multiply. Can we issue the multiply? No, we're still trying to issue the load. And the multiply is going to require F2, which is a hazard on the previous load. So we can't issue the multiply either. But now the integer pipeline's done on cycle 4. So what are we going to issue now?
The load.
Okay, we'll issue the load. Can we issue the multiply?
Yes.
Yeah, we should do that next cycle. Yep. So let me go step back just to show you what's going on. Whoop, load. Destination is F2. We're going to use R3. We can load the next one into the multiply unit, mult, destination F0. We have our 2 operands, and of course, we are basically waiting on the energy unit to complete from previous. Right.
Why are we waiting on the integer unit?
So FU, wow, that was terrible. Functional unit. Oh my goodness. All right. Where was it? I need to write these up and print them for you.
Yeah.
Source register numbers for the register read. And remember, this is a write after read check. QJ and QK. Producing the source registers FJ and FK. This is really a wake up. Are we producing it? And then these are flags. FI is the destination. FJ, FJ, AK are the 2 that we're being read from. QJ and QK are producing the source registers. For something up here. Do you need to do any type of forwarding?
Okay.
Okay, good. Right, that's integer because remember it's waiting for the F2 to complete up here so it can execute. Do you see?
Yeah.
You issued it to multiply, but it's saying I'm waiting for the previous integer, aka this guy, to complete before I can do mine.
All I read was the FU and not the QJ.
Oh, okay.
So I was like, what?
Oh, well, that makes sense. So we can issue the multiply, but can't read F2 until the load completes. But we've at least issued it. It's waiting in the execute stage. It's just being stalled. So we can actually look at the subtraction as well, because we've gone through these guys. We can look at subtraction, F8, F6, and F2. Can we issue that? Well, okay, obviously we can issue them. Are there any issues we have?
The F2, you need the wait to write to it.
Right, it needs to be written first before that can start executing. So he's been issued to the floating point add unit, but he's still waiting for the load to complete so he can do something. Notice up here I'm telling you at what cycle things enter. Read multiple, no, F2 is not ready. So next would come divide. So on 8, can we issue the divide? Or I need to stop telling you this. But what's going on with the divide?
That's 0 waiting for it to operate.
Yeah, waiting for the multiply to complete.
Yeah.
Yeah.
Multiply 1 to complete. Notice how mult 1 and right here, waiting for it to complete. It's keeping the scoreboard. All right, how about the add? DDD. Yeah. Add double. Floating point
It's
add.
ready, right?
What's that? Can we issue it?
Yeah.
Well,
That's 6.
we can't issue it. Why can't we
No,
issue
we
it?
can't because it's still waiting for a subtraction.
Yeah, because it's currently busy. So we can't do anything yet. But I believe at this point the load finally completes. Load completes, update mult D and sub D, waiting on F2. So they're ready to go because those 2 are correct. They're good. So this is the time remaining. Multiply takes 10 cycles, add takes 2. So let's go ahead and go forward a couple. Boom. Oop. Can we read the operations for multiply and subtraction? Yes, because they're both legit now, because they've been written back, so we can read them. All right, cycle goes by, mult has 9 cycles left, add has 1. Now add has 0 cycles, so it's been executed. What's going to happen next?
Go back a step. Okay, not going back a step.
So notice on this cycle, add mark complete, because that's the subtraction.
Mm-hmm.
What's going to happen next?
The subtraction.
Right, so the subtraction can, or the add D, well, say that again. You almost got me to say it. Good job.
I want to say what?
Go ahead, what happens next?
I don't know. I lost track.
What instruction were we trying to issue?
When
The when instruction. Nice. So we have the divide. What about the add?
Oh, yeah.
Can he be issued? Not this cycle, but this guy is about ready to be complete.
Yeah.
So then he can be issued. Do y'all see that?
Mhm.
We were stalling right here the whole time because the add unit was busy.
Oh, yeah.
So we're going to go ahead and try and put the add in. Okay, in scoreboarding, yeah, there is a 1 cycle delay because it has to be cleared out and then it can be added the next time.
Cool.
So read for the div D. No. So back here, let's go. Nope, I didn't tell you. The add completes, but we still can't do anything with divide, is what this is pointing out, because F0 is still not available, because that's the destination for this guy. So the divide is still waiting, but we can put in the add. Is the add ready to go? Yes. In this one, he uses F8 and F2. Which we've already gotten rid of with the previous, well, that's a read, sorry. F8 has already been written to by the previous subtraction, and what is it, this, he's the add. The divide is writing F10, so you're fine, and the multiply is writing F0. So that add is good. You can also tell because I put yes, yes right here. So he's going to execute. Add completes. Notice we were able to complete this add while the divide hasn't even started executing yet because he's waiting on that multiply. So we are able to keep going down the instruction list and find new instructions to put into our pipeline and actually do some useful work. That's what out-of-order execution, why it's so powerful. So we'll keep going. Oh yeah, why don't we write the result of add? Ooh, there's a good question.
Because the subtract is using it? No. Because divide's using it.
Let's see. It's running to F6 because, yes, you're correct. Because divide is using it, and that would make a write after read error because it would be writing this add, even though the read needs to happen before it. So
And
the way
it's not cool.
so the way Scoreboard fixes that is it just stalls the add. And this is where my slides become awesome and stop working. So 1 moment.
Oh, what was that fancy feature?
What, escape, go forward 1?
It looked like there's a thing highlighted on there.
Alright, so the multiply, still waiting for that to complete. Multiply finally completes. What happens after the multiply finally completes?
Takes a cycle to clear out.
Okay, takes a cycle to clear out. Well, kind of give it to you. What else happens though? What else, who else is going to get cleared at that time?
The divide.
The divide's going to be clear. These two guys are ready to go. So we're going to have the divide start executing.
Divide, add now.
Yeah, and then after the divide starts executing, because the divide will then have his right answer inside its functional unit, then you can commit the add. So you have a cycle to get the divide ready to go. He's no because he's executing. War hazard is gone, so we can complete the add. The war hazard, huh? All right, and well, divide takes 40 cycles. Right, down to 0. Little time warp. 61, he's finished, and then divide is gone. Okay. Any questions on this? Do y'all see how the hazards were solved by just stalling it out?
Is there a faster way, a better way of doing it? So it's all-
Doing this? Oh yeah. Way better way of doing this.
The turtle method.
But this is probably the intuitive way. Don't issue the instruction until it's ready to go, which is what this scoreboard is doing, is keeping a scoreboard of what's going on. All right, so took 62 cycles. All right. In order issue, out of order execution, and out of order commit. Excuse me, commit. Because notice we committed the add before the divide was done. So the commit was out of order as well. but the execution was out of order as well. Okay. Historical context. Yes, Matt?
Looks interesting.
They got a speed up of 1.7 from a compiler, 2.5 by hand. They didn't have caches back then. Right, I know. Whoa. Well, they could have had one, but they didn't, because they didn't. There was no need at that point. All right, limitation of the 6600. No forwarding, limited to instructions in basic block, small window, because it could only really look so far ahead before it just stopped. Small number of functional Unix. This is because of 6600. It do not issue on structural hazards, wait on war hazards, and prevent. But it did prevent the write after write hazards by basically holding it in the functional unit till it was done. All right, precise interrupts. The idea. Okay, let me see if I can answer this for you now. Precise interrupts. Precise interrupts is if an interrupt comes in, can you just clear everything and then be good to go? Does that happen in this one? Did it happen in your in-order pipeline? Let's start there. If you need to interrupt everything, could you just clear it and then you'd be good to go? You know, just flush the whole pipeline right off the bat, flush everything with no ops, and then you'll be okay?
Sure.
Yeah, you could be. But the problem here, when you have this add is committed. Let's say the add's been committed. You're in the middle of a divide and you get interrupted. When you get restarted again, you're going to start at this divide, which is going to reissue the add. Y'all see what I'm saying?
Mm.
So it's not a precise interrupt in scoreboarding. You would have to have extra hardware to take care of that. We're just going to leave it at that. Just keep that in mind.
That sounds great.
Yeah.
You should say that.
And leave it at that. Just know that that's even another problem. All right, IBM 360. Okay, we're going to talk about Thomas Sulos next. I'm going to go ahead and pause the video.